and cosinus just in a derivative. So I even didn't pay attention to this 1, 0, and 2.
Let me see. So,
just like derivative. I did it just like a derivative, and that's it.
So
like
let me just
cosinus became minus sinus.
let me just differentiate this function with respect to x1 first. So we have d over dx1, and we are differentiating f of x just with respect to x1. And we are going to evaluate this at x0. So let's see. This is a constant, and that also is a constant. We are just differentiating with respect to x1. The other terms are just constants. So what I will have is, I will have cosine squared of x2 over sine of pi over x3 times the power 3 times the argument with an power just decreased by 1. So this is your derivative function. And if I'm going to evaluate this function at x is equal to 0, I should just plug in 1 to here. 1 squared is 1. And 0 to x1, which will just make this cosine of 0. And cosine of 0 is 1. And then 1 squared. This part is just 1 squared again. And then I have 2 here. So I should just plug in 2 to here. I have pi over 2. Sine of pi over 2 is 1. So this is 1 squared over 1 times 3 times 1 squared. Then this is just equal to 3. And that's the first question. So do we have any issues on this question? Should I repeat anything? Do you have any questions about it?
Teacher, I have a question.
Yeah, shoot it.
So here the cosinus will not be a minus sinus, yeah?
No, because it's just a constant.
It's just like be constant.
It's the term with x2, not the term with x1.
I thought like the thing that we had at class, like cosinus became minus sinus and sinus became a cosinus x, and I did like this.
I see. So the question actually was simple. You just had to be calm down and observe carefully and see that all the trig functions are just functions of other variables that we do not take care about on that point. So the second question again uses the function f. Here we are asked to find the gradient of f evaluated at x0. We should find this. We already have the first derivative function with respect to x1. So the first derivative with respect to x1 is cosine squared of x2 over sine of pi over 2, and we have a 3 here, and we have x1 squared here, and then we just plugged in our numbers. So this is a 0 and this is a 1, and that's equal to just 3. So this is the derivative with respect to x1 evaluated at x0. And then let's continue with the, I'm sorry, I'll just copy this formula to this page below so I can continue nicely. So this is f of x, and now we should differentiate it with respect to x2. So now I'm going to compute d over dx2 f of x evaluated at x is equal to 0, x0. So I'm trying to find this now. This is going to be something like this. This is a term with x1. This is a term with x3. These are just constants. Here I have x1 cubed over sine of pi over x3. And then this constant is followed by the x2 term here, which is cosine squared of x2, which requires a chain rule operation. So this is just 2 times cosine x2 times negative sine of x2. And now I'm going to evaluate this at x0, and x0 is, let me just write it too. So x0 is 102 transposed. So I'm going to plug in 1 to here. So this is 1 cubed, which is 1. This is x3. When I plug in 2 here, this is going to be a 1, 2. So this whole chunk is just a 1. And then I get negative 2 times cosine of 0 times sine of 0. And you know that sine of 0 is 0, so this chunk is gone too, which means this is going to be equal to 0. Any problems on this differentiation? All right, then I will just continue with the third derivative. This is my function again. F of x is x1 cubed times cosine squared of x2 over sine of pi over x3. And what I'm asked to find is, I should find d over dx3 f of x evaluated at x0. So let me just do it. And when I begin, I see that this is just a constant and that is another constant. And I can just rewrite this function as I have x1 cubed times cosine squared of x2 times sine to the power negative 1 of pi over x3. Is this clear? Are you guys there? Can you hear me?
Yes, teacher.
Okay.
It's clear.
So now I'm going to differentiate this, and when I differentiate it, I will just preserve this first chunk as is. So it's going to be x1 cubed times cosine squared of x2. Then I'll just write down the power, negative 1. I will just decrease the power by 1, negative 2, and rewrite the outer function. Then I will write the inner function differentiated. So the inner function is just sine of pi over x in 3. So sine of pi over x3 is cosine of pi over x3. And I have one more thing to do. So I have one more inner function here, and that is going to be pi times negative 1 times, let me see, x3 squared. So this is your derivative function. Now I'm just going to plug in the numbers. Let me start from the left. When I plug in 1 here, this is going to be a 1 cubed. Then I'm going to plug in 0 here, and this is going to be a 1 squared. And then I have a negative 1 here, and when I plug in 2 here, this is going to be 1 over negative 2. And when I plug in 2 here, the cosine term will become cosine of pi over x3, which is cosine of pi over 2, and that's going to be a 0. And then I will stop computing the rest because this 0 will make the whole chunk a 0. So this is a 0. And then finally I can just rearrange the gradient function evaluated at x is equal to 0. And this is gradient of f evaluated at x0. It's going to be 3, 0, and 0. Any questions about question 2?
No question.
All right. So let me just continue with the third question. Well, this is just x as I, the Greek letter. You can read it as z, g of z. It doesn't matter, you can just replace it with x if it just looks weird to you. It doesn't matter. Let me just solve this question. You're asked to find the Hessian matrix of function g evaluated at z0. So let me just do it. Here we have the question, so we can work easily. Let me start. So the Hessian of g evaluated at x0 is something like this. d squared dx1 dx1 g of x evaluated at x0. This is your first element. Then you're going to have d squared dx1 again, but now the second differentiation will be with respect to x2. G of x evaluated at x0. Then in the second row, the differentiation starts with respect to x2, followed by x1 for the first element, evaluated at x0 again, and finally d squared over dx2 dx2 g of x evaluated at x0. So this is going to be your question. You should compute 8 derivatives for this question. So let's begin with the first one. I will first try to compute d over dx1 g of x, and when I try to do this, I see that here I have a term of x1 and then I have a term of x2. The term with x2 is just a constant, and a constant differentiated is just 0 for me. Then I will just concentrate on the first chunk here. Here I have sine of x1 over cosine of x1, or I have sine of x1 cosine to the negative 1 of x1, whichever looks easier to you. And when I differentiate it, using the product rule, I will first differentiate the first term, the sine of x1 part here, which is going to be a cosine of x1. The second term remains as is. This is cosine to the negative 1 of x1. Then I should leave the first term as is, sine of x1, and multiply it with the second term differentiated. It's going to be negative 1 times cosine raised to the negative 2 of x1. So I can just rearrange this as this is just the same thing, and it's going to be 1. And this is just, let me see. I'm sorry, I forgot something here. So sorry. I should have a negative sine of x1 too. So that's what's missing there. So then the two negations just cancel each other out. I have a sine squared of x1 here over cosine to the negative 2 of x1 here, which actually is just secant squared of x1. So that's it for the first term. The thing is, if I'm going to differentiate it one more time with respect to x1, I can do something. But if I'm going to differentiate it with respect to just x2, then this guy is going to be a simple 0. Let me just continue a little bit more. Let me just compute the second term and its differentiation.
Teacher, I'm sorry, I have a question.
Yeah, shoot it.
Teacher, how tangents became sinus? Because, like, I just write positive sec square x1, and you mentioned here sinus and then cosinus, like, how it became like this?
This is just another version of it, but you should just first do it like this one. It is easier to comprehend with. If you like, I can do the quotient version of it too. It is more...
Okay, teacher, but as you mentioned, the derivative of tangents will be like sec square x. So
it is.
positive.
So and that is right here.
Yes. Yes, but like I'm just concerned about sinus and cosinus. Like, where did it come from?
It came from the formulation of the tangent function. Tangent simply is sine over cosine. And sine over cosine is a quotient, or you can also write it as a product too. And you can just use one of the two formulas, whichever seems easier to you. This is harder to compute, easier to comprehend. This is easier to compute, harder to comprehend. They are just the same thing. Because this is just 1 plus 10 squared of x, which is just secant squared of x. You should know the transition from 1 plus 10 squared x to the secant squared of x.
Okay, teacher, thank you.
Most welcome. So for the second one, I should just compute this guy. And I'm sorry, I don't have extra space here, so I have to just create it first. Let me just push it down and continue here. I think what we had is something plus 0.2 times x2 squared. Was it something like this? Let me just check it again. No, it was cubed, not squared. So this was the function g of x. I didn't write this part. This is because this is just something of x1, and I am going to differentiate this with respect to x2. That's why I didn't care about that part. And let me just write it down. This one differentiated is O dot 2 times 3 times x2 squared. And please notice that this answer does not contain any term of x1. And if you are going to just differentiate it with respect to x1 to get this guy, what you're going to end up with is a simple 0. Are the zeros clear? So there's something in the chat. Let me see it. Okay. Then my next job is differentiating with respect to x1 again and x2 again for both functions. This was what I had originally. D over dx1 of g was equal to 1 plus 10 squared of x1. And d over dx2 of g was equal to 0.6 times x2 squared. Then d squared over dx1 of g is just equal to 0 plus 2 times tangent of x1 times secant squared of x1. This is by the chain rule. And for the second term, d squared dx2 dx2 of g is just equal to 0.6 times 2 times x2 to the power 1. So it's just 1.2 times x2. And I can just plug these in. And when I do that, what I'm going to get is this is tangent of 2 times tangent of x1 times secant squared of x1. These two are zeros, and the last one is 1.2 times x2. Let me just check the question and get the values for them. The first value for x1 is going to be a pi, and the second one is going to be 5 over 3 square rooted. So let me just plug in these values. And when you just plug in these values, you get 1.2 times square rooted 5 over 3. And for this guy, the tangent of pi is going to be a 0, and this whole chunk will become a 0 too. And that's it. So let me just continue with the fourth question. Okay, so for the fourth question, I will use the Desmos graphic calculator. So let me just get to the web page first. So this is the graphic calculator, and that is going to be your function sine of x minus 2 squared plus 0.4 x. So this is your function. What you're asked to find is slice of this function. To get the slice of that function, I should just read the function first. I'm sorry, the domain first. So, yeah, that's it. So it tells me that I may spend from $0 to $7. So the domain is 0 to 7. Then 0 greater than or equal to why can I not write it down? Yeah. 0 greater than or equal to x, and this is going to be a 7 too. So that's your function. And let's get back to the question now. The first question is, how many critical points does H have for the given domain? So it is just a simple counting operation for this question. So this is a critical point, this is 2, and all the peaks and bottoms for the wiggling function are critical points. So let me just count them. 1, 2, 3, 4, 5, and yeah, 5 peaks and 1, 2, 3, 4, 5 bottoms. So we have 10 critical points. That is the answer for question 5A or 4A. Let me just check. 4A. The second one is, how many extrema does H have for the given domain? Let me see. Extrema are either critical points or margin points or the points where the limit is not defined. So this is going to be a margin point, and this guy is going to be another margin point. We don't have any points where the limit is not defined, so the answer is 12, 10 plus 2. We just added the margin points. Let me continue with 4C. Let me get to the question first. 4C is, what are the values of H evaluated at the margin points? Let me just check. So this is one margin point, and the value of the function is negative 0.757. This is the first part of your answer, and 7 is another margin point, and the function evaluated at 7 is 2.668. That's the second part of the answer. And the final sub-question is finding the range of this function. So this margin point is the global minimum. I do not see any other point that is smaller than negative 0.757. And conversely, this point, roughly 6.5, is the global maximum. Our function evaluated at 6.5 will give me roughly 3.6, which is the greatest possible value, the global maximum of the function. Thus, the range is from negative 0.7 to positive 3.6, and that's it for the fourth question. Let me just get to the fifth question. Or do you have any questions about question 4? Let me ask that first.
Teacher, I have a question.
Yeah, shoot it.
Teacher, what's the difference between global maximum and local maximum?
All right, so it is about the definition. Let me just get you the definition first. So where is my mouse? I have just found it. And yeah, here it is. So for local maximum, you're just around the point within a small neighborhood. There are no xn's that are smaller than your x0 around the neighborhood within a small range. This is for the local maxima. On the other hand, for global maxima, you say that there are no xn's that are greater than x0 in the whole domain of the function. Is it clear now?
Yes, teacher. So we cannot say that they are the same, yeah?
The global maximum is actually a local maximum, but the local maxima does not have to be the global maximum points.
Okay. Okay, thank you, teacher.
The local optimas are just relatively good solutions relative to the neighborhood around them. They are not the best answer to the question. And do we have any other questions? Okay, then let me just continue with the fifth question. If I can get to that file, yeah. For the same function h, starting from 1.8 and with a step size of 0.1, we are asked to iterate twice using the appropriate gradient search algorithm. So let me just revisit the fourth question and see how h is defined. So here it says that h is a profit function, which just imply that the greater values for h is favorable. Then we are trying to just maximize this function. So I'm going to just perform 2 times the gradient ascent function. Let's just do that. And I think I don't have much time left. Let me just slowly do it. So this is the update function. The new solution xk is equal to the previous solution xk minus 1 plus, since this is the gradient ascent function, the function differentiated with respect to x evaluated at xk minus 1. So this is just the first order derivative information times the step size. Let's start. I have to find x1, which is equal to 1.8, because it says starting from 1.8, and f of 1.8 differentiated times 0.1. So this is your update function to find x1. what I just don't know is the derivative function of f evaluated at 1.8. So let me just get that using the Desmos graphic calculator. I will just say that this is f of x. And then this is f prime of x, which is the derivative function. And this is f prime of x evaluated at 1.8. So this is just a very, very, very small number. I will write it as 0.00032. So this is 1.8 plus 0.00032 times 0.1. And then it's just going to be 1.80032. So I didn't move much far, and that's it. Let me just hold on for a moment and wait all the guys to just get back online. Okay, now I think we are good to go. So this is just the first update. Do you have any questions with the first update? Do you? Okay, then let me just continue. Then I will proceed forward to find x2, which is going to be 1.80032. This is the x1 plus f of x evaluated at 1.80032 times alpha, which is 0.1. And again, I don't know what this is. Let me just plug in that in the value and find out using the Desmos graphic calculator. So let's just write 3 zeros, 1 3, and 1 2 here. Then I will just get 3 zeros, 1 3, and 1 8. Let's get back to the question. So this is 1.80032 plus 1. I'm sorry. This is wrong. Plus 0 times 0.00038 times the step size, which is 0.1. Then the answer will become something like this. This is 1.8, and then the 8 is followed by 3 zeros, 1 6, and 1 7. That's it. The thing is, we have just moved by 0.0000 and 7. This is how much we moved from our initial solution. So it does not change practically. This is your first takeaway. This is 5A. Let me just continue with 5B. 5B says, starting from x is equal to 0, using the same step size, iterate once using the appropriate gradient search algorithm. The appropriate gradient search algorithm actually is the gradient ascent algorithm. Then x1 is going to be x0 plus f prime of x0 times the same step size 0.1. Let me just plug in the values. This is 0. Here I need to find f prime of 0 times 0.1. Let me just find what is the function f differentiated and evaluated at x0. So let me just plug in 0 here. This is 3.015 roughly. So this is going to be something like this. 0 plus 3.015 times 0.1, which will get us 0.3015. So with a single iteration, we have moved like 300 times faster than before. And let me just get to the final version. 5C says, for the sub-question, for the same sub-question, change the step size to 0.05 and reinitiate from x0. Now we are going to have x1 is equal to 0 plus 3015 times 0.05. So let me just compute that. 0 plus 3.015 times 0.05, which is weird. Maybe I should make these dots commas. Yeah, this is better. So it's going to be 0.15075. So this is going to be 0.15075. It is similar, it is roughly half the distance we traversed before with the greater step size. And then the sub-question D asks, how would you describe the situation you observed at sub-question A? So in sub-question A, f differentiated around 1.8 was roughly 0. What is the name of this situation? Do you remember? Do you remember the name of this situation? Okay. This is called the vanishing gradient problem, because the update function formula is something like this. The new solution is the old solution plus or minus f differentiated at the old solution times the step size. And when the derivative is 0, this whole chunk is roughly 0, and the new solution is roughly the old solution, so there are no updates. This is called the vanishing gradient problem. Do you remember now? Do you remember it now? And I'm proceeding with the sub-question E. Considering B and C, which step size would be more appropriate? Explain and mention the formal definition of derivatives within your reasoning. Well, I think you should always remember the formal definition of derivatives, which is something with the limits. So this is the formal definition of derivatives. F prime of x0 is equal to limit h goes to 0 f of x0 plus h minus f of x0 over h. So this is the rate of change, actually, when the change is converging 0. Since in this formula we set h very, very, very small, you should always pick the smaller step size instead of the larger one. So this is not a great choice, and this should be a better choice. Is this clear? Okay. Let me just proceed with the sixth question. In the sixth question, we are asked to compare gradient search algorithms with the calculus-based approaches for multivariable functions. The information is we have a multivariable function whose argument has 1000 components. Then, just to compute the gradient of f, you need 1000 derivatives. This is the first order information. One derivative for each element of the argument vector. So you have 1000 partial derivatives. Then, for the Hessian function, for each first order partial derivative, you will have 1000 more derivatives. Then you're going to have 1000 times 1000 derivatives for the Hessian. So this is going to be 1000 squared more derivatives. And the final version is, if you get a critical point, you should just be able to differentiate it and classify it as a local minimum or a local maximum. If the point is a local minimum, then the Hessian should be positive semi-definite. And the positive semi-definiteness test requires computing the determinants of each principal minor of the Hessian, and a Hessian with 1000 rows and 1000 columns has 1000 principal minors. Then the PSD test needs 1000 determinant calculations. So that's it. For this test, for just one critical point, you are going to calculate 1,002,000 derivatives and determinants. Let me call this 1,002,000 steps. Let's keep this in mind and continue. And with 10 different starting points and using the gradient descent algorithm, how many iterations can I make? So this should be greater than 10 starting points, 10 times the number of iterations. So the number of iterations should be less than 100,200, and that's it. This is your answer to the 6th question. Let me just continue with the 7th and the 8th questions. Question 7 says, explain the vanishing gradient and the exploding gradients, referring to the gradient search algorithms, offer solutions to both cases. Well, we have just talked about the vanishing gradient case, where the first order derivative information is approximately 0 and the function does not update. On the other hand, the exploding gradient is just the opposite of this situation. So here we have xk, the new solution, and we have the old solution, xk minus 1, minus, since it says the gradient descent, the first order information evaluated at k minus 1 times alpha. Well, this is the term that makes the change, and whenever this guy is roughly positive or negative infinity, then the difference between the new solution and the old solution is again roughly infinity. So it just blows up like a bomb and teleports you to some unknown region of the function. Maybe that region is not even in the domain. So it causes convergence problems. And for solutions, a simple idea is to just restart the algorithm with distinct starting points, as just mentioned in question 6. This was for question 7. And for question 8, it just informs you about a quality management approach, a continuous improvement approach named Kaizen, the Japanese approach. And it defines Kaizen as taking small steps towards a better direction, hoping for small improvements instead of big breakthroughs. So how does this relate to what you have learned in this course? So the calculus approaches is trying to teleport you to good solutions, local optimas. On the other hand, the local search algorithms just moves slowly and steadily towards better solutions. So that's the short explanation for question 8. So that was your exam. Do you have any questions now? You may also ask in Turkish too, by the way. And let me just say one more thing. The answers for 5, 6, 7, and 8 was just mentioned right before the exam on our last recitation hour. So it is on the 9th at 7:30, I think. Any other questions? Okay. So we don't have much time, but if you like, we can just talk about our lecture notes, which I have sent you and asked you to read it. Did you read those lecture notes, the handouts? If you have done it, you can ask me questions about the unclear parts, and we can just make them more clear for you. Yok mu arkadaşlar sorunuz soracak?
Hocam şu son 5, 6, 7, 8 için ne dediniz onu kaçırdım da ben.
Sınavdan önceki son ek derste bunların hepsinin cevabını yapmıştık dedim. Tam olarak bu arada.
Teşekkürler.
Rica ederim. Sorusu olan var mı arkadaşlar? Yoksa ben hızlıca ders notlarınızın üzerinden geçeyim. Becerebilirsem açmayı. Evet. Şimdi bunun üzerinde hızlıca konuşabiliriz. Since you don't have any questions about your exam, I will just fly slowly over your handouts. So what we have learned in this semester is using either the calculus or the local search approaches to get better solutions for our decisions. And to be able to do that, we have started talking about linear algebra essentials for it. The first thing we have talked about was the linear algebra objects. We have named 4 of them. We have named the scalars, which basically are just numbers. We also have vectors. Vectors are just list of numbers. And we have named matrices. Matrices are rectangular array of numbers, and they also can be interpreted as list of transposed vectors like this one. This is just a transposed vector. And lastly, we named tensors. Tensors are the generalization of the linear algebra objects. The scalar, the vector, and the matrix are tensors actually. A scalar is a zeroth order tensor. A vector is a first order tensor, and a matrix is a second order tensor. So it is just about high dimensional data storage. And then we started talking about something that looks like absolute value for vectors, which is the length of the vectors. And to measure this length, we covered two different norm metrics. They were L1 norm and L2 norm, or you may remember me calling them the Manhattan distance or the Euclidean distance. The L1 norm simply is the sum of absolute values of each element in a vector, whereas the L2 norm is just the Pythagorean distance, the triangular distance from one point, from one vector to another. And here, one of the vectors is always the point of origin. Then we also talked about the Hadamard product. The Hadamard product is also known as the element-wise multiplication. Here is an illustration, you can just see it. This is 1 times 4, 4, 2 times 5, 10, and 3 times 6, 18. We also talked about the determinants of square matrices. So the determinant is denoted by det A or absolute A for matrices. And it is, let me say, the directional volume of a matrix. So this is a weird term, directional volume. If you're into linear algebra, you can just ask me later on what that means. Then we talked about the principal diagonal. It starts with the northwest and ends up with the southeast corners. And we also talked about the principal minors. So you always keep the first element in the principal diagonal and grow around it slowly. The first principal minor is the northwest element. The second principal minor is the first neighbors around the northwest element. The third principal minor is the first and second neighbors around the northwest element, and it goes on and on until you get the whole matrix. So this was the linear algebra essentials for our course. Do you have any questions about this part?
Teacher, I have a question.
Yeah.
Teacher, Hadamard and multiplication rule, they are not the same, yeah?
Yeah. So the Hadamard product and the dot product. The Hadamard product is a circled dot, V times, let's say, Q. And the dot product is V dot Q. The notation is a little bit different. This guy is the dot product or the matrix multiplication. And this means something else. So if you have the prices, P, and the quantities, Q, then P transpose times Q will give you the revenue. Each price of the quantity sold for each product multiplied together and then summed up. Is it clear now?
Yes, teacher. So as you mentioned at university, we cannot multiply 1 by 3 and 1 by 3.
Exactly. So that's why P is transposed in the dot product.
Okay. Thank you, teacher.
Most welcome. So that was all about linear algebra. And then we started talking about single variable differential calculus. And we had a different approach. We didn't just dive into the computations. Instead, we started our journey from talking about the difference between relations and functions. So a relation is not a deterministic situation. So let me call this beta of x0. This beta of x0 may give me -2 or 3. So it may have multiple outcomes. It may also just give me pi. So we don't like relations because it doesn't provide a firm grip on the phenomenon. We cannot just control the problem easily using relations. But on the other hand, for functions, you always get one exact output for each value x0. This is the difference. So it gives you more power over the situation. So we like functions more, that's the reason. And you may just remember the good morning example we talked about in the class. It is also written here. Then we have the function notation here. We read this f brackets x as f of x. And here f is just the name of the function. Traditionally, functions are named after single letters. And x is the argument of the function. We may have a vector as the argument, but this is not the case for single variable functions. And functions are also called mappings of x to. So you just map x to some outcome, to some output value using the function f. And for that reason, sometimes functions are denoted just like this. F assigns the domain to the values in the range. And here, the capital D is the set of all possible values of x, the argument. And the capital letter R is the all possible values f can be outputted, f can assign. So all the possible values of the function is called the range, and all the possible values of the argument is called the domain. So for divisible decisions, the domain is generally the set of real numbers or a slice of it. On the other hand, for non-divisible decisions, affirmation or negation of something, you say either yes or no to something, or hiring some people to the company. These are indivisible, these are indivisible and countable arguments. Then the domain is generally either the set of integers or a slice of it. So in the set D, in the domain set, the boundary values is called the margin points. So this is all about the notation of functions. Then I have a small section about data-driven decision making here, or in short, DDDM. So data-driven decision making is just using data to make better decisions. That's it. And let me just remind you the turnover rate example. So what may just explain the turnover rate? Faulty hiring decisions, loss of motivation due to constant negative feedbacks, sexual harassment, mobbing, lack of internal personal bonds or strong external bonds, relatively low wages, bad company reputation, and so on. We may have many reasons for high turnover rate. And collecting data on this phenomenon will help you get control over the situation and fix the high turnover rate and save your company. Now let's talk about the concept of rate of change. So here we had some arguments. I just wonder, what happens if I just lower the level of mobbing, psychological harassment, within my company? I just wonder how my function reacts to this action. And I measure this effect using the concept rate of change. So let's assume that x0 is the current level of mobbing within my company, and h is the action, the result of action that I took, which just lowers the level of mobbing. If this change is large, I may just jump from one region, one good region of our function to another. And making great changes suddenly may not be always possible. That's why, instead of taking big steps, we just employ small changes at a time. That's why h goes to 0 in this definition. And by the way, as you also know, this just is the formal definition of single variable derivatives, the first order derivative. And the derivative at some point is the slope of the function at that point. What do you mean by the slope? So we are trying to lower the high turnover rate we are experiencing. If I get a negative slope, then when I increase that argument, my function just gets lower and lower values. Or if I get a positive slope, then when I increase that argument, I get greater values of the function. So, in this case, the slope for the mobbing should be positive. When you increase the rate of mobbing in your company, the speed of people leaving you also increases. They don't like your company that much after the change. So this means I should keep mobbing at a minimum, and I should take actions towards it. That's it. And this is just explained here on the concepts steepest ascent and steepest descent. And then we talked about differentiability. In order to a function be differentiable, there should be No breaks, no elbows. So let me just illustrate it. So this is just a break. And that is an elbow. On the other hand, this is a smooth transition. So we like this guy, and we don't like these guys. They are not differentiable. Is it clear up to now? Do you have any questions about data-driven decision-making, functions, relations, or differentiability? So I have to just restart the Zoom session. Our time is up. Do you guys have any questions up to now? Do you guys have any questions before I proceed? Okay, so no response. I will wait a little bit more for other people to just get back online. Then I will continue. Maybe not everyone is coming back. Okay, so let's continue talking about the extremum points and why they matter. The plural form of extremum points is called the extrema. And to be able to define what an extremum point is, I should first explain what a neighborhood is. And let me just try to draw it. So this is your function, and this guy is just x0. And when you just magnify this region, you will see that x0 lives around some place with a radius epsilon. And this is called the neighborhood of x0. When this epsilon goes to 0, you get the neighborhood around the values around x0. So that's the neighborhood. The small region of that function around x0. Is the concept neighborhood clear now? I hope so. Let me just continue. Extrema are important because the extremum points are local optimas, or in other words, local maximum points or local minimum points. Let me just explain these concepts. So our current position is x0. And I claim that f of x0 is the smallest possible value, and there are no xn's that are smaller than x0 around the neighborhood of x0. So if this is the case, then x0 is the local minimum. Similarly, if there are no greater values xn's around x0, then x0 is a local maximum. So for local optima, these values are relatively good within their neighborhood. On the other hand, for global optimas, there should be no better solutions xn's within the set of domain. There should be no better solutions within the domain. So at first, I was restricted to the neighborhood of x0. Now I just expand this along the domain. So global means best. That's it. And local means better. Maybe this helps. The extremum points fall into three categories. They may be the points at which the limit is not defined. They may be the critical points, or they may be the margin points. So the extremum points are what we look for. They are the candidates for good solutions. Now let's talk about differential calculus a little bit more. Let's talk about first order derivatives and their interpretation. Well, if the first order derivative is non-negative, either positive or zero, then f is non-decreasing around that point. If the first order derivative is strictly positive, then the function is increasing around that point. If the first order derivative is exactly zero, then the function is constant or stationary around that point. If a function is non-increasing, if the first order derivative is non-positive, either negative or zero, then the function is non-increasing around that point. And finally, if the first order derivative is strictly negative, then the function is decreasing around that point. So this is how you use first order derivatives to learn how your function behaves, whether it's increasing, decreasing, or stationary around some points. On the other hand, let's assume that the function f is stationary around x0. And you have opposite signed first order partial derivatives around x0. Then your x0 is either a local minimum or a local maximum. So let's just illustrate this version. It tells me that f is decreasing when we approach x0 from the left. So So this is x0. F is decreasing from the left, and f is increasing from the right. Then, as you can see, this x0 is a local minimum. Similarly, if f is increasing when you approach x0 from the left and decreasing when you approach x0 from the right, then x0 should be a local maximum point. But these are just kind of fuzzy terms. How much do you approach x0? By how much? That proximity metric is not given to you, and that's why this is just a little bit fuzzy. And you need the second order test to eliminate this fuzziness. One other thing we are going to talk about is when the first order partial derivative is either both positive signs or negative signs around some critical point, then that's a ledge point. And this is a ledge. Let me just draw it. So it is increasing, it is stationary, and it's then increasing again. The reason you call this ledge, parvas, is you may just put some pots and grow some plants in front of the window. That's why we call this a ledge. It's increasing from the left, it's increasing from the right, it's stationary at x0. So that's a ledge point.
Teacher, I'm sorry, I have a question.
Yeah, I'm listening.
Teacher, ledge point and inflection point, are they the same? It's
Ledge
like
points are always inflection points, yes. The answer is yes.
Okay, thank you.
But inflection points are not necessarily ledge points. I will get to that. And I will give you just one example first. So this is my two-dimensional space, and here I view f of x, and this is x, and this guy happens to be my function, which is simply parallel to the horizontal axis. And at this point, the second order derivative is just zero everywhere. And the first order derivative is also zero. But this is not a ledge point. This is just a linear function. But weirdly, this is an inflection point by definition. And
so teacher, inflection point can be in a constant line. It is not only concave and convex.
Any subpart of a function that behaves linearly is an inflection point.
Okay, I thought only concave and convex, like the
not necessarily. Any region that behaves linearly.
Okay.
And let's now talk about the second order derivatives. If the second order derivative is strictly positive, then you are in a convex region. Even if your function is decreasing at first, it will just become increasing because it increases at a faster pace. That is what it means when you have positive second order derivative information. So, and we may also observe negative second order derivatives, even if your function is increasing at first, it will eventually stop and become decreasing. You have 1/3 option. Your functions may be just linear, not changing its slope. Then the second order partial derivative information is 0. This is how you use second order derivative information. Because, well, this guy is a local minimum, and that guy is a local maximum. And these guys are nothing. This is how you classify your critical points, if you have one, into the classes local minima or local maxima. And then we may also have non-critical points. For non-critical points, inflection points are transitions from convex regions to concave regions or vice versa, like this one. So let me just draw an arbitrary function here. Here it behaves convexly, and then it just changes its mind and starts behaving concavely. Just the opposite. I said it wrong. In this part, it is concave, and at this part, it becomes convex, and this is your inflection point. Do you have any questions about first order derivatives or second order derivatives?
Teacher, if we have a critical point, our f of x is always equal to 0. Am I right?
I'm sorry, just can you repeat it again?
If we have a critical point, our f of x is always equal to 0. Am I right?
So having a critical point just means your function is stationary around some point. So let this be some critical point here, and let this be another critical point, and that be another one, and this be our final case, which is the constant function. So in these cases, my function is at nothing. This is not a local maximum nor a local minimum. This is a local maximum. This is a local minimum. This is both a local maximum and a local minimum because there are no smaller values around it. There are no greater values around it. But they are not zero valued. So that part is irrelevant. The function should not be zero valued. For critical points, the first order derivative of the function is zero valued. This is 0, not the function itself.
And teacher, in second order derivative, if it is negative, that means it is 0 or it is like concave?
When the second order derivative is negative, you have something similar to this, which means the function is curving downwards, which means at some point it will reach a local maximum point. So this is concave. I'm sorry. This is concave and that's a local max. Does it answer your question or was it something else?
No, it is concave. Yeah, I got it. But is it equal to 0 or it is not equal to 0?
Well, it is not equal to 0. It's negative. The second order partial derivative information is negative around this local maximum point.
Thank you.
Most welcome. Let me just move on and let me just find my cursor. Yeah, here I found it. And this was about the calculus approach to find critical points, which are extremum points, within which we are searching for local optimum points. But we have one other option. Instead of using the calculus-based approaches, you may also use the local search algorithms, which is, within the domain, you just pick some initial solution. It doesn't have to be good, it doesn't have to be bad, just a random one. And from that random solution, you try to find a direction which will get you better solutions. And through that direction, you move just one step and repeat the process. Decide the direction, move one step. Decide the direction, move one step. Decide the direction, move one step. Hopefully, at some point, you will get a really good solution. This is the rationale behind the local search algorithms. And you also know that the first order partial derivative information actually is the steepest ascent direction for that function at that point. Which means when you increase the argument, your function will increase the most, or when you decrease the argument, your function will decrease the most. This is the first order derivative information. You have one more option. If you negate the first order derivative information, if you take the negative of the first order derivative, then you get the steepest descent direction, which actually is the direction that decreases our function the most. When I increase my argument, I know that f will decrease the most. Or when I decrease my argument, f will increase the most. So this is how I decide the direction using the first order partial derivatives. Also, one other thing I mentioned was the step size. I was taking one step at a time. So these steps may be just gigantic or very, very small. Since from the formal definition of partial derivatives, let me just revisit that definition. From the formal definition of partial derivatives, you know that the change should be very, very small, and that change happens to be the step size in the local search algorithms. I'm sorry, I will get there. Okay. So, if you use the positive version of the first order partial derivatives, then you apply the gradient ascent algorithm and try to maximize your function. And if you use the negative of the first order partial derivative, then you use the negative descent algorithm and try to minimize your function. And here are the update functions. So the new solution xk is something added to the current solution xk minus 1. And that something you add is a step towards the first order derivative. This is the update function for the gradient ascent function. Similarly, For the gradient descent algorithms, a new solution is the current solution minus something, and that something happens to be a step towards the negative of the first order partial derivative information. Do you have any questions about the logic behind the local storage algorithms or the update functions for the gradient ascent or descent function algorithms? Okay. Assuming no, I just proceed. Now I will talk about the two common problems you may just come across to using the local search algorithms with the gradient-based directions. The first one is the vanishing gradient problem. That is, the second term of the update function, this guy, is just the product of the first order partial derivative. And when the first order partial derivative, this guy, approaches 0, then the difference between the new and the old solutions are just 0. And the other version of it is the exploding gradients, which means when your first order partial derivative approaches infinity, either positive or negative, then the difference between the new and the old solutions just goes to infinity. So this is just a bomb. And this is just a snail. This is the difference between the vanishing gradients and the exploding gradients. Is it clear?
I'm sorry, teacher, I have a question.
Yeah.
Teacher, here is infinite. So what do you mean by infinite? It is just like infinite with numbers, or?
I just mean huge number. So let me just illustrate one example for exploding gradients. So this is an asymptotic function. And around this region, when you approach the point from the left, the derivative is approximately infinity. And whenever you approach the function from the right, then the first order partial derivative approaches approximately negative infinity. And then, when you plug in that value to the update function, either plus or minus, infinity times alpha, which is infinity, and then this is just infinity. So that's the problem. It just blows you up and teleports you to some unknown region of the function.
Okay, now it's clear.
And now let's start talking about multiple variable functions. Let's start with the simple case, the scalar valued single variable functions. This is what you are familiar with. You have a function of a single argument, and the function is expressed as a mathematical formulation. This is just a single variable function. Then we may have scalar valued multiple variable functions. And now the argument is not a scalar, not just y, but a vector which has many components. Then the function is something like this: x1 plus, x2 plus, blah blah, something of x3, x5, xn, it goes on and on. So it is a function of many variables, several variables. And we also have a final version of it. You again have an argument vector, but this time you have capital F of x, which contains many subfunctions. Let's say m of them. Let me just try to explain the practicality of this. So we try to identify some things that affect the turnover rate, the faulty hiring decisions, loss of motivation, and so on. If you just take control over the situation and start manipulating these arguments, yeah, it's straightforward. You're going to just mend the situation, you're going to lower down the turnover rate, and your company should be happy. But this is a little bit short-sighted, because when you manipulate this many things, the turnover rate is not the single thing that gets affected. There may be some other functions of these arguments. For example, the profit, or the cost, or the productivity, or the public image of the company, and on. So, considering the simultaneous effect of your actions is wiser. That's why we are trying to talk about multivariable functions. And in this case, I should redefine the formal definition of partial derivatives. For single variable functions, it just looked like this. So I changed x0 by h and observed the effect of that change. Now, I'll just try to observe the effect of change in just one component within the argument vector. So that's the trick. And let's assume that, for this case, I'm trying to observe the effect of change in x1, the first component. Then, I just have to use a filter vector, for which only the first element is 1 and the rest of it is 0. And I will just multiply h using the Hadamard product operation with this filter vector, so that I observe the effect of change in just x1 and assume all other things equal, constant, not changed. So this is the reformulation of the partial derivatives for multivariable functions. If you just use the k-index, denoting this is the kth subfunction in a vector-valued multivariable function, then things just become like that. It's very similar. So this is the general formula for multivariable functions and their first-order partial derivatives. There's some other thing I should mention, and that is the length of I, this filter vector, should be always 1. Let me just continue. Let's talk about the use of first-order derivatives. It's very similar. If the first-order derivative information is zero-valued for all functions with respect to all arguments, then you have a critical point. But this time, for m subfunctions and for n arguments, you are trying to set things to 0 for m times n components, which is harder. And that's why finding critical points in multivariable functions is not that likely as it is in single variable functions. But let me just introduce the notation. The gradient vector is the first order derivative information for scalar valued multivariable functions. And this vector is a list of first order derivatives with respect to each argument. And the Jacobian matrix, on the other hand, is the first order derivative information for vector valued functions, which is the transpose of gradient vectors arranged in a list. That's it. So you can just see that. I'm sorry. Yeah. For first subfunction, this is the partial derivative with respect to x1. This is the partial derivative with respect to x2. And it goes on to the final element, the partial derivative with respect to n. And then you do it for the second subfunction, third, and it goes on until the mth subfunction. You're not going to do that many work on Jacobians, but this is important. So please try to remember that. So the rest of it is very, very similar. If the first order derivative information is positive, then f is increasing. If it is non-negative, then f is non-decreasing. If it is 0, then f is stationary. If it is non-positive, then it is non-increasing. And finally, if it is strictly negative, then f is decreasing. So this is the interpretation of first order derivatives. But let me just introduce you to two weird regions in multivariable functions. So let me just try to illustrate in one dimension. So this is f of many x's, and this is just one of them, say x2. And this is how x behaves. Well, it has been increasing, then it became stationary, then it started to decrease. Well, this region is a plateau, a relatively high stationary constant region. And one other option you can just observe is something like this. It is decreasing and then it becomes constant for a while, then it start increasing again. And this region is a valley. The regions that behave linearly with zero slopes in multivariable functions. These are problematic regions for local search algorithms. That's why they're important. But you are not responsible for the region, but you can just say it. Since the slope is zero, there is vanishing gradient around these points within these regions. I have to just restart the session because our time is almost up. So let me just wait for a moment for everyone. Okay, I think we are ready. So about the second order derivatives for multivariable functions. For scalar valued multivariable functions, for each first order partial derivative of a function f of argument vector x with n components, you're going to have n first order partial derivatives, as we have seen in the gradient. And then for each of these first order partial derivatives, you're going to have n second order derivatives, like this one. Differentiated first with respect to x1 and then with respect to x1 again. First with respect to x1, then with respect to x2. First with respect to x1, then with respect to xn, and on and on. If you arrange the second order partial derivative information like this, then you get a Hessian matrix of F. And since this matrix shaped second order partial derivative information is not a scalar, it's not straightforward to tell whether you are in a convex region or a concave region. You cannot easily say that the second order partial derivatives are strictly negative or positive or zero. To be able to do that, you have to just evaluate the function at the point of interest, at x0, and along the principal diagonal, test the determinant of principal minors, starting from the northwest element and slowly growing around it until you get the whole matrix. If all these determinants are non-negative, then you say that the Hessian of F is a positive semi-definite matrix, and around x0 you have a convex region. Well, this is really hard work. If you have, say, 100 arguments, then you're going to have 100 partial derivatives for the gradient. Then 100 squared for the Hessian. Then 100 determinants to test the positive semi-definiteness. And, well, if Hessian is not positive semi-definite, then no luck. It's not a local optimum. You start over again, try to find some other critical point, if at all it exists. So this is a not fruitful, hard work to find good solutions. But what can you do? What should be a good strategy to move around it? Well, it is using the gradient-based search algorithms again. And moving towards the good directions, you slowly get better and better values. And if you use multiple initializations with distinct solutions, then you may get different, relatively good solutions. And maybe one of them is the global best. It is never guaranteed, but who knows? Maybe you can just catch it. So that was the whole summary of this semester. Now I ask, finally, do you have any questions?
Teacher, is this information is enough for passing the exams?
It was enough for the finals. It will be enough for the retake exam too.
Okay, teacher, thank you.
Most welcome. But the important thing is this clear to you?
Yes, now it is clear.
Yeah.
Actually, teacher, I already studied everything, but even though I couldn't pass, so I will, I hope I can do better.
Well, I believe you all will do better, but here's the thing. Math was the lowest grade in my whole undergraduate transcript. It doesn't mean that I'm bad at math. It just means I just needed, in that past time, I just needed more time to get things right. So you may just get bad scores now, it doesn't matter. The important thing is this information is really, really valuable. It is just a summary of maybe 2,000 pages I have written while I was studying at Stanford, MIT, Michigan State University, University of Michigan, Georgia Institute of Technology, Bill Kent University, Hacettepe University, Top University, and here. So it is an extremely valuable summary. I hope eventually it will just kick in. So if you don't have any more questions, I will just conclude this session. So do we have any more questions? Okay. Then see you all at the retake. Bye-bye.